What if I told you the universe isn't just a cold, empty expanse, but something far stranger? Picture this: galaxies stretching across the void like neurons firing in a cosmic brain, black holes pulsing with eerie regularity like a heartbeat, and vast clouds of gas swirling as if breathing in and out. These aren't just poetic comparisons, they're real, observable phenomena that make scientists pause and wonder, could the universe itself be alive in ways we're only beginning to understand? Today, we're diving into 36 jaw-dropping moments where the cosmos didn't just resemble life, it seemed to imitate it down to the smallest detail. And what we've discovered will forever change how you see the fabric of reality. Think about the last time you looked up at the night sky. Those pinpricks of light aren't just scattered randomly, they're part of an intricate web, a galactic network so similar to the neural pathways in our own brains that researchers have dubbed it the cosmic connectome. It's as if the universe is wired together like a colossal nervous system, exchanging signals across billions of light years. Then there's the rhythm of quasars, flickering with such precise timing that it mirrors the steady thump of a pulse. And let's not forget how galaxies spin and collide, their movements uncannily like cells dividing in some grand celestial organism. These parallels aren't coincidences, they're clues pointing to something deeper, something almost unsettlingly profound. So what does it all mean? If the universe behaves like a living thing, does that make us mere specks inside its vast body, or something more? Over the next 20 minutes, we'll unravel these mysteries one by one, from the way dark matter flows like blood through cosmic veins to the haunting possibility that black holes could be the universe's way of recycling energy, just as living creatures recycle nutrients. By the end, you'll see the night sky not as a static backdrop, but as a dynamic, ever-changing entity, one that might just be more aware than we ever dared to imagine. Buckle up, because this journey will stretch your mind to the very edges of what we know and beyond. The cosmic web isn't just a pretty arrangement of galaxies, it's a blueprint, a master pattern that repeats itself from the smallest scales to the largest. Those glowing filaments stretching across the darkness, they're not random. They mirror the branching neurons in your brain with such precision that if you placed an image of a brain cell beside a map of the universe, you'd struggle to tell which was which at first glance. Scientists call this phenomenon structural similarity, and it goes far beyond mere visual coincidence. The way galaxies cluster along these threads, how they knot together at intersections, it's all governed by the same mathematical rules that shape the growth of fungal networks in soil, the spread of veins in a leaf, even the way information crackles between synapses in your mind. Take the Perseus-Pisces supercluster, for instance, one of the longest known filaments in the observable universe. It spans over 1 billion light-years, a river of galaxies flowing through the void. Now zoom in. Your brain's white matter forms eerily similar pathways, bundles of axons transmitting electrical signals. The resemblance isn't superficial. Researchers at the University of Bologna ran simulations comparing the two, and the statistics lined up almost perfectly. Both systems optimize for efficiency, balancing connection and distance, minimizing energy expenditure while maximizing information flow. It's as if the universe keeps rediscovering the same architectural principles, whether it's building a brain or weaving galaxies together. And here's where it gets eerie. These patterns emerge from entirely different forces. Neurons connect through biochemical processes, while galaxies are strung together by gravity and dark matter. Yet both systems self-organize into near-identical shapes. This suggests something profound. there might be universal laws of network formation that transcend scale and substance. Whether you're looking at the internet's infrastructure, the spread of slime mold, or the universe's grand design, the same invisible hand seems to be at work, an underlying logic that favors certain structures over others. So what does this mean for us? If the universe and life share these deep structural echoes, it hints that we're not just inhabitants of the cosmos, we might be expressions of it. Like a fractal where every level reflects the whole, from the spin of electrons to the whirl of galaxies, the universe appears to be playing variations on a single, magnificent theme. And if that's true, then every thought you have, every memory, might be a tiny echo of the same patterns that knit the cosmos together. Black holes don't just consume, they transform. Like a living cell absorbing nutrients, these cosmic giants pull in gas, stars, even light itself, breaking it all down into something new. But here's the twist, they don't hoard everything they swallow. Just as cells expel waste, black holes blast out colossal jets of energy, shooting particles across galaxies at nearly the speed of light. These aren't random outbursts, they're precise, almost rhythmic, like a biological process fine-tuned over eons. And the event horizon, that's no simple boundary. It functions like a semi-permeable membrane, controlling what enters and what gets flung back into the cosmos, a delicate balance between intake and expulsion that mirrors the way living systems regulate their internal environments. Consider the supermassive black hole at the center of Galaxy M87. Its jets stretch for thousands of light years, twisting through space like tendrils. Now compare that to the way your body's cells manage energy, taking in oxygen and glucose, releasing carbon dioxide and water. The parallels are startling. Both systems take raw materials, extract what's useful, and eject the rest in highly organized ways. Even the math behind these processes overlaps. The equations describing how black holes accrete matter bear an uncanny resemblance to models of nutrient absorption in single-celled organisms. It's as if the universe has a favorite recipe for energy conversion, whether it's happening in a microscopic mitochondrion or a gravitational behemoth with the mass of billions of suns. Then there's the way black holes multiply. When two collide, they create a new, more massive singularity, an act that eerily parallels reproduction in living systems. The resulting gravitational waves ripple outward like a cosmic birth announcement. Some theorists go even further, suggesting that black holes might seed new universes inside their depths. A speculative but tantalizing idea that casts them as cosmic parents rather than mere destroyers. If true, it would mean these enigmatic objects aren't just recycling energy within our universe. They could be spawning entirely new ones, a life cycle operating on scales we can barely fathom. So what's really going on? The more we study black holes, the less they resemble simple vacuum cleaners of space, and the more they act like dynamic, almost metabolic engines. They don't just erase matter, they reconfigure it, repurpose it, sometimes even rebirth it. This isn't destruction, it's transformation on a grand scale. And if black holes are indeed the universe's recycling centers, it raises a humbling possibility that the atoms in your body might have once passed through one of these cosmic furnaces, forged anew in an endless cycle of death and regeneration. The universe doesn't waste, it reinvents, and in that sense, perhaps it's more alive than we ever dreamed. Deep in the cosmic void, spinning neutron stars called pulsars keep perfect time, beaming radiation across space with the precision of a Swiss watch. These ultra-dense stellar corpses rotate hundreds of times per second, their lighthouse-like beams sweeping past Earth in pulses so regular you could set your clock by them. But contrast that with quasars, the hyperactive cores of distant galaxies whose light flickers wildly like an erratic heartbeat. Together, they form a celestial rhythm section, one orderly and predictable, the other chaotic and explosive. The strange part, both phenomena appear to follow patterns eerily reminiscent of biological systems, as if the universe is running on cosmic circadian rhythms. Take the famous crab pulsar, born from a supernova witnessed by Chinese astronomers in the year 1054. Every 33 milliseconds without fail, it sends a pulse racing toward Earth. That's faster than a hummingbird's wings beat. Meanwhile, quasars like 3C273 flare up and dim over months or years, their brightness dancing to a tune we're still deciphering. What's fascinating isn't just the rhythms themselves, it's how they emerge. Pulsars owe their precision to conservation of angular momentum, a fundamental physics principle where spinning objects resist slowing down. Yet that same principle governs the whirling of water down a drain or the spiral of a falling maple seed. The universe seems obsessed with recycling the same patterns across wildly different scales. Then there's the glitch phenomenon. Occasionally, a pulsar's steady beat will stutter, its rotation suddenly speeding up before settling back to normal. Astronomers compare it to a heart skipping a beat. These glitches may occur when the neutron star's crust cracks under immense pressure, like tectonic plates shifting, or when superfluid vortices inside the star suddenly rearrange themselves. Either way, the effect is unnervingly lifelike. Quasars exhibit their own version of arrhythmia, with some flaring randomly while others show quasi-periodic oscillations, mathematical patterns that resemble everything from earthquake tremors to the electrical surges in epileptic brains. So are these just superficial similarities or clues to something deeper? Some theorists propose that the universe self-organizes through feedback loops akin to biological homeostases. Just as your body regulates temperature or blood sugar, galaxies might balance energy output through mechanisms we're only beginning to detect. Others argue it's simply physics repeating its favorite tricks, like a composer reusing motifs in a symphony. But here's the provocative thought. If both living organisms and cosmic objects exhibit rhythmic behavior governed by similar mathematical principles, could there be a shared language of vibration underlying all reality? From the spin of electrons to the pulse of quasars, the universe hums with hidden cadences, and we're just starting to listen. Dark matter doesn't just lurk in the shadows, it moves. Like an invisible river coursing through the cosmos, this mysterious substance flows in vast, intricate channels, weaving between galaxies and stitching the universe together in ways we're only beginning to map. Picture the circulatory system in your body, veins and arteries branching into capillaries, delivering oxygen to every cell. Now scale that up by billions of light years. Dark matter operates on a similar principle, its gravitational tendrils funneling gas and dust into galaxies, feeding star formation like blood nourishes tissues. Without it, the universe as we know it would collapse, a cosmic body starved of its vital scaffolding. The evidence is etched into the night sky. When astronomers study galaxy clusters like the Bullet Cluster, they see the aftermath of dark matter's invisible hand. Two galaxies collided, their visible gas slowed and heated by the impact, but their dark matter kept sailing right through, leaving a gravitational imprint detectable only by how it bends light behind it. The result, a ghostly silhouette of dark matter, separate from the visible wreckage, like tracing the outline of a vein beneath skin. This shadowy architecture isn't unique. Simulations show dark matter forming a cosmic web, with filaments intersecting at nodes where galaxies cluster, mirroring how blood vessels converge at organs. The resemblance is so striking that astrophysicists have borrowed terms from biology, describing dark matter flows as feeding galaxies and nurturing star nurseries. But here's where it gets stranger. Dark matter doesn't just shape galaxies, it syncs with them. Studies of spiral galaxies reveal their rotation speeds defy Newtonian physics unless dark matter is woven into their fabric like a gravitational mesh. It's as if every galaxy wears an unseen exoskeleton, a halo of dark matter that stabilizes its spin. Even our Milky Way moves to this hidden rhythm, orbiting the galactic center at speeds that would fling stars into the void without dark matter's anchoring pull. This delicate balance, visible matter dancing to dark matter's tune, parallels how your body regulates blood flow, adjusting pressure and distribution to keep every cell functioning. Could dark matter be more than cosmic infrastructure? Some theorists speculate it might interact in ways we haven't detected, not just gravitationally, but through faint forces akin to biochemical signals. Others propose it could decay over eons, releasing energy like metabolic waste. While these ideas remain speculative, they underscore a tantalizing truth: the universe doesn't just contain life. Its fundamental structures echo life's blueprints, from the branching of trees to the firing of neurons. Dark matter, invisible and enigmatic, might be the universe's way of keeping itself alive, a silent, pulsing network that breathes order into chaos, one galaxy at a time. The spiral arms of the Milky Way don't just swirl, they whisper a secret about the fabric of reality itself. That same graceful curve appears in the unfurling of a fern, the whirl of a hurricane, even the branching of your own capillaries. This isn't just artistic coincidence, it's evidence of a cosmic fingerprint, a repeating pattern so universal that mathematicians call it a fractal, a shape that echoes itself at every scale, from the infinitesimal to the infinite. What if these fractals aren't just mathematical curiosities, but something far more profound? What if they're the universe's version of DNA, an embedded code dictating how everything grows, from galaxies to snowflakes? Take the humble Romanesco broccoli. Its conical florets spiral outward in perfect logarithmic spirals, each tiny bud a miniature replica of the whole. Now zoom out to a galaxy like Messier 74, its arms spinning in that same precise spiral. The equations describing both are nearly identical, despite one fitting in your palm and the other spanning 80,000 light-years. Even more startling, the Fibonacci sequence, that mathematical pattern found in sunflower seeds and nautilus shells, also governs the distribution of matter in galaxy clusters. It's as if the universe has a favorite formula, stamping it across creation like a cosmic signature. But here's where it gets eerie. DNA itself is fractal-like. The double helix twists in a spiral, while the folding of chromosomes follows fractal geometry to pack meters of genetic material into a microscopic nucleus. This parallel raises a tantalizing question. Could the universe store information in its fractal patterns the way cells store blueprints in DNA? Some theorists speculate that fractal networks, like the cosmic web of galaxies or the branching of lightning, might encode fundamental laws of physics, a kind of source code for reality. After all, both DNA and fractals excel at one thing: efficient replication. Your cells divide using genetic instructions, while galaxies grow by following gravitational patterns etched into the cosmos since the Big Bang. Consider the Mandelbrot set, the infinitely complex fractal generated by a single equation. Zoom into any part of it, and you'll find smaller copies of the whole, nesting like Russian dolls. Now look at satellite images of river deltas or the veins in a leaf. They mirror this same self-similarity. Even the distribution of craters on the moon follows fractal statistics, matching the clustering of matter in the early universe. These echoes suggest an underlying order, a set of rules that transcend scale and substance. Whether it's the branching of trees or the sprawl of galaxy superclusters, the universe keeps returning to the same architectural principles. So is this just nature being lazy, reusing the same templates, or something more intentional? The answer might lie in entropy, the universal tendency toward disorder. Fractals represent a loophole in this rule. They create immense complexity from simple rules, maximizing structure while minimizing energy. A single equation can generate a universe of detail, much like a seed contains the instructions for an oak. If the cosmos truly operates this way, then fractals aren't just pretty patterns, they're survival strategies, optimized over billions of years. The spiral of a galaxy conserves angular momentum, just as the spiral of a seashell conserves resources. Efficiency becomes artistry, and the universe reveals itself as both engineer and poet. Perhaps the most humbling thought: we're made of this same fractal poetry. The air in your lungs branches fractally to maximize oxygen absorption. The neurons in your brain form fractal networks to process information. Even your heartbeat fluctuates with fractal rhythms, balancing predictability and adaptability. You aren't just observing the universe's patterns, you're woven from them, a living expression of its deepest blueprints, and that changes everything. If fractals truly are cosmic DNA, then every spiral galaxy, every crashing wave, every synapse firing in your brain is part of an infinite recursion, a universe writing itself into existence, one self-similar stitch at a time. Deep inside the Orion Nebula, a stellar nursery 1,300 light-years away, newborn stars flicker to life like cosmic fireflies. These aren't just balls of gas igniting. They're part of a grand, almost biological process. The nebula's swirling clouds of hydrogen and dust contract under gravity, forming dense knots that eventually ignite into stars, a sequence eerily reminiscent of cells dividing in an embryo. And just as a placenta nourishes a developing fetus, the nebula feeds its protostars with streams of gas, channeling material through filaments that look uncannily like umbilical cords under a microscope. The universe doesn't just create stars, it gestates them. Consider the Eagle Nebula's pillars of creation, those towering columns made famous by Hubble's lens. Inside those pillars, radiation from nearby stars sculpts the gas, triggering collapses that birth new suns. It's a violent, beautiful process, like a cosmic version of labor pains. But here's the twist: when stars die in supernova, they blast heavy elements back into space, enriching future generations of stars and planets. This isn't just destruction, it's a cycle, a celestial inheritance where the remains of one star become the building blocks for the next. In that sense, every atom in your body was forged in the heart of a long-dead star. You're literally made of stardust, recycled across billions of years, a living testament to the universe's reproductive rhythm. The parallels go deeper. Stars don't form in isolation. They're often born in clusters, siblings emerging from the same cosmic womb. Over time, gravitational interactions scatter them across galaxies, much like offspring leaving home. Some, like our Sun, wander alone. Others remain bound in binary systems, twirling around each other like twins holding hands. Even their life spans mirror biological organisms, short-lived massive stars burning bright and fast, while smaller red dwarfs smolder for trillions of years, the cosmic equivalent of tortoises outliving mayflies. But the most haunting similarity lies in the numbers. The Milky Way produces about 7 new stars per year. Extrapolate that across the observable universe's 2 trillion galaxies, and you're looking at a staggering rate of stellar birth, a universe constantly replenishing itself. Some theorists even suggest that black holes, those enigmatic endpoints of massive stars, might be cosmic seeds for new universes in a multiverse scenario. If true, it would mean stars aren't just the universe's children, they're its parents too, part of an infinite generational loop where death begets new beginnings. So is star formation mere physics or something more poetic? The equations describe collapsing gas and nuclear fusion, but the patterns whisper of a deeper continuity. From the Fibonacci spirals of galaxies to the pulse of variable stars, the universe seems obsessed with repetition, with cycles within cycles. When you look up at the night sky, you're not just seeing points of light, you're witnessing a vast, breathing ecosystem, one where stars are born, live, and die in rhythms that feel strangely, intimately alive. Imagine two particles born from the same quantum event, now separated by the width of a galaxy. Yet when you tweak one, its partner responds instantly, as if no distance exists between them. This isn't science fiction, it's quantum entanglement, the phenomenon Einstein famously dismissed as spooky action at a distance. But what if this eerie connection isn't just a quirk of physics? What if it's the universe's way of maintaining a cosmic nervous system, linking every corner of existence faster than light could ever travel? Picture your brain for a moment. When you decide to move your hand, neurons fire, sending electrical signals racing down your spinal cord at speeds of about 200 miles per hour. Now zoom out to the cosmic scale. Entangled particles behave like neurons synced across light years, reacting in perfect unison without any detectable signal passing between them. It's as if the universe has its own version of synaptic transmission. Bypassing the speed of light limits the way your thoughts bypass the need for physical bridges between ideas. Take the groundbreaking experiments conducted at the University of Geneva. Scientists entangled pairs of photons, then sent them racing through fiber optic cables to villages 18.6 miles apart. When one photon's quantum state was altered, its partner mirrored the change instantaneously, faster than a beam of light could have bridged the gap. This phenomenon holds true whether particles are separated by meters or galaxies, suggesting a fundamental interconnectedness woven into reality's fabric. Some theorists propose this could hint at higher dimensions where distance is an illusion, or a holographic universe where every part contains the whole, like a single neuron holding the blueprint for the entire brain. But here's where it gets provocative. If entangled particles communicate without exchanging conventional signals, could this mechanism underlie a kind of universal awareness? Philosopher David Chalmers once speculated that consciousness might be a fundamental property of reality, like mass or charge. In this view, entanglement wouldn't just link particles, it might facilitate a cosmic-scale flow of information, a silent dialogue between all things. Even black holes, those devourers of information, may preserve entangled connections through Hawking radiation, as if the universe insists on keeping its thoughts intact. Of course, not all scientists embrace such metaphysical interpretations. Mainstream physics often treats entanglement as a mathematical curiosity, a consequence of quantum mechanics' probabilistic rules. Yet the parallels are hard to ignore. Just as your brain's coherence emerges from billions of firing neurons, the universe's large-scale structure, its galaxies, dark matter webs, even the uniformity of the cosmic microwave background, might rely on quantum connections threading through the void. So are we part of some vast thinking cosmos? The answer remains elusive, but the question itself reshapes our place in the grand scheme. If entanglement binds the universe together like neural pathways bind a mind, then every particle in your body is in silent conversation with the farthest quasar. You're not just in the universe, you're of it, entangled in its rhythms, its whispers, its hidden dialogues. And that realization doesn't just expand our understanding of physics, it blurs the line between the cosmos and consciousness itself. Gamma-ray bursts aren't just cosmic fireworks, they're the universe's reset buttons. For a split second, these explosions outshine entire galaxies, releasing more energy than our Sun will in its 10-billion-year lifetime. But what if their purpose goes beyond sheer destruction? Imagine a forest fire clearing dead wood to make way for new growth. Gamma-ray bursts might serve a similar function on a galactic scale, sterilizing regions of space so future generations of stars can emerge. It's a brutal process, but one that mirrors how immune cells target infections, sacrificing damaged tissue to protect the whole organism. Take the gamma-ray burst known as GRB 080319b. When it detonated in 2008, its jet carved through a nearby galaxy like a scalpel, ionizing gas clouds and disrupting star-forming regions. Yet within a few million years, a blink in cosmic terms, those same areas saw a surge of new stellar births. The burst had effectively cleared cosmic blockages, much like white blood cells removing debris from a wound. Even the distribution of these events seems deliberate. Gamma-ray bursts occur more frequently in metal-poor regions of the universe, areas where stars haven't yet cooked heavier elements. This selective targeting hints at a self-regulating system, pruning back overgrowth where it could choke future development. But here's the chilling part. These bursts might also enforce galactic quarantine. When a gamma-ray burst erupts, its radiation can sterilize planets thousands of light-years away, wiping out potential life in its path. Some researchers suggest this could explain the Fermi paradox, the puzzling absence of alien civilizations. Just as immune responses prevent pathogens from spreading, gamma-ray bursts may reset regions where life grows too abundant, preventing cosmic ecosystems from becoming overcrowded or unstable. It's a sobering thought. The universe might have its own version of herd immunity, and we're only here because our corner of the Milky Way hasn't faced a recent outbreak. Yet there's a twist in this cosmic immune analogy. Unlike biological systems that react to threats, gamma-ray bursts appear pre-programmed. They're triggered by the deaths of massive stars or collisions of neutron stars, events written into the universe's laws from the beginning. This suggests a deeper design, not just reactive cleanup but proactive maintenance. The cosmos doesn't wait for problems to arise. It builds in safeguards, like a body equipped with autoimmune protections before birth. So are these bursts destructive or creative? The answer might be both. Just as inflammation heals as it burns, gamma-ray bursts could be the universe's way of balancing chaos and order. They remind us that even in the vastness of space, nothing exists in isolation. Every cataclysm is part of a larger rhythm, a pulse of destruction and renewal that keeps the cosmic organism alive. Stars don't just shine, they breathe, not in the way you and I inhale oxygen, but through a process so fundamental it underpins the entire cosmos: nuclear fusion. At their cores, stars fuse hydrogen into helium, releasing energy in a rhythmic pulse that keeps galaxies luminous for billions of years. This isn't just combustion, it's stellar respiration, a slow, steady exhalation of photons that bathes planets in warmth. Now zoom out. The universe teems with these radiant engines, each one converting matter into energy with the precision of 1 trillion microscopic power plants. Together, they form a vast metabolic network where energy flows like blood through celestial veins. But stars are only half the story. When they die, the most massive ones collapse into black holes, cosmic recyclers that don't just consume energy, they redistribute it. Picture a supermassive black hole at a galaxy's heart, devouring swirling gas like some insatiable mouth. Yet these monsters aren't wasteful. Their intense gravity heats incoming material to millions of degrees, creating quasars that beam energy across space like cosmic lighthouses. Even their event horizons aren't one-way streets. Through Hawking radiation, black holes slowly evaporate, returning energy to the universe over trillions of years. It's a cycle as elegant as cellular respiration: intake, transformation, release. Then there's dark energy, the universe's most mysterious fuel. Unlike stars or black holes, it doesn't emit light or absorb matter. Instead, it permeates empty space itself, accelerating the cosmos expansion like an invisible exhale pushing galaxies apart. Some theorists compare it to a background metabolism, a silent, omnipresent force governing the universe's growth. The numbers are staggering. Dark energy constitutes nearly 70% of the universe's total energy budget, dwarfing everything from stars to planets. Yet its effects are subtle, detectable only in the redshift of distant galaxies fleeing from us faster every second. This cosmic energy exchange mirrors biological systems in uncanny ways. Your body breaks down glucose, extracting 38 molecules of ATP per sugar molecule. Stars achieve similar efficiency, converting about 0.7% of their hydrogen mass into energy via Einstein's famous equation. Even the waste products align. Just as your cells produce carbon dioxide, stars forge heavier elements like oxygen and iron in their cores, scattering them across space when they explode. These elements become the raw materials for planets and life. The parallels grow deeper when you examine scale. A single human cell contains roughly 1 billion ATP molecules, each storing energy for about a minute before being recycled. Now imagine the universe's ATP, photons streaming from stars, gravitational waves rippling from colliding black holes, even the faint glow of the cosmic microwave background. These carriers move energy across light years, connecting cosmic structures in an intricate web of exchange. The difference: your body's metabolism runs on chemical bonds. The universe's runs on space-time itself. So is the universe truly alive? Maybe not in the way we traditionally define life, but the evidence suggests something profound. The cosmos operates like a self-sustaining organism, governed by cycles of energy transformation that echo biology's deepest principles. From the fusion furnaces of stars to the dark energy stretching the void, the universe doesn't just contain energy, it dances with it, trades it, reinvents it. And in that endless exchange, we find ourselves temporary sparks in an eternal flame. Time moves in one direction not because clocks say so, but because the universe insists on it. Everywhere we look, from shattered teacups to dying stars, disorder increases. This relentless march toward chaos, known as entropy, isn't just a law of physics, it's the universe's version of aging. Think of a tree growing from a sapling to a towering oak. Its structure becomes more complex, its branches more intricate, but with time, rot sets in. The universe follows the same arc. After the Big Bang's fiery birth, it cooled and clumped into galaxies, stars, and planets' order emerging from chaos. But like an organism's cells gradually wearing out, every transformation leaks energy, every motion radiates heat into the void. The cosmos isn't just expanding, it's slowly exhausting itself. Consider the fate of our sun. 4 billion years from now, it'll swell into a red giant, then collapse into a white dwarf, its energy spent. Meanwhile, the universe at large will continue stretching, galaxies drifting apart until their light can no longer bridge the gaps. This isn't mere expansion, it's growth on a cosmic scale, like a child's bones lengthening into adulthood. But growth has limits. Eventually, stars will burn out, black holes will evaporate, and space itself will approach absolute zero, a state physicists call heat death. No more energy to extract, no more work to be done. The universe, in essence, will have died of old age. Yet here's the haunting twist: entropy isn't just a countdown clock. It's what makes life possible. Without this irreversible slide toward disorder, energy wouldn't flow, chemical reactions wouldn't occur, and DNA couldn't replicate. Your body is a temporary rebellion against entropy, a pocket of order sustained by sucking energy from your surroundings. Stars do the same, delaying their demise by fusing atoms. Even Earth's ecosystems are entropy battlegrounds. Plants capture sunlight to build sugars. Predators consume prey to maintain their bodies. The universe's aging process, ironically, creates the conditions for fleeting islands of complexity like us. Could time itself be biological? Some theorists speculate that the arrow of time emerges from quantum interactions, much like consciousness arises from neural networks. Others see dark energy's acceleration as a kind of cosmic puberty, a phase shift in the universe's development. There's even a controversial hypothesis that black holes might spawn new universes in their cores, making time cyclical rather than linear. If true, our universe could be one generation in an infinite lineage, born from the death of another. The evidence is written in the sky. When we observe distant galaxies, we're peering into the universe's youth, seeing light emitted billions of years ago. The further we look, the younger the cosmos appears, its past preserved like rings in a tree trunk. And just as trees add layers in response to their environment, the universe's structure, its galaxies, voids, and cosmic web bears the scars of ancient collisions, explosions, and expansions. Time isn't just passing, it's accumulating, building a history as rich and layered as any biography. So is the universe alive, not in the way we define life. But the parallels are too striking to ignore. It grows, it ages, it transforms energy in cycles that mirror metabolism. And one day, like all living things, it will reach its end not with a bang, but with a whisper of heat dissipating into infinite stillness. Yet even in that final equilibrium, there's a strange beauty. The universe, having lived its story, becomes the silent ground from which new stories might emerge. Time's arrow points toward entropy, but along the way it carves out moments of breathtaking order. Planets, stars, and beings capable of wondering about it all. At the heart of nearly every galaxy, including our own Milky Way, lurks a supermassive black hole, not as a destructive force, but as a cosmic stabilizer, a gravitational anchor that shapes its host galaxy's very existence. These black holes, weighing millions to billions of times the Sun's mass, aren't random accidents. They're integral to their galaxies, much like mitochondria are to our cells, powerhouses that regulate energy flow and maintain balance. The relationship is so finely tuned that astronomers now see galaxies and their central black holes not as separate entities, but as partners in a billion-year dance of mutual dependence. Take the galaxy Messier 87, home to the first black hole ever imaged. Its colossal jet, stretching 5,000 light-years into space, pumps energy into the surrounding galaxy like a heart pumping blood. But here's the remarkable part. The energy output of that jet matches the galaxy's star formation rate almost perfectly. Too much energy and stars couldn't form, too little and gas would collapse chaotically. It's a feedback loop as precise as the way your body regulates temperature, a cosmic thermostat ensuring equilibrium. This symbiosis goes deeper. Studies show that the mass of a galaxy's central black hole correlates tightly with the size of its galactic bulge, the dense cluster of stars at its core. The ratio is astonishingly consistent across the universe, whether the galaxy is a petite spiral or a giant elliptical. It's as if galaxies and their black holes grow together, like trees and their root systems, each shaping the other's development. When black holes feast on gas, their explosive outbursts called quasars can heat surrounding material, preventing runaway star formation that might otherwise exhaust a galaxy's fuel too quickly. In this way, black holes act like cosmic pacemakers, setting the rhythm for galactic evolution. But what happens when this delicate balance falters? Look at the galaxy Markarian 1018. Its black hole, after gorging on matter for eons, has entered a dormant phase, and the entire galaxy has dimmed, its star formation sputtering like an engine running out of fuel. Meanwhile, galaxies with overactive black holes, like the quasar 3C273, blaze with radiation so intense it strips gas clouds of their ability to form stars entirely. These extremes reveal the black hole's dual role, both nurturer and enforcer, fostering growth while preventing excess. The parallels to biology are irresistible. Mitochondria, once free-living bacteria, became embedded in our cells 2 billion years ago, trading energy production for shelter. Today, they're inseparable from our biology, just as black holes seem inseparable from galaxies. Some theorists even suggest that black holes could be catalysts for complexity, their gravitational influence funneling gas into regions where stars and potentially life can arise. Without them, galaxies might remain formless clouds, never coalescing into the structured spirals and ellipticals we see today. So are galaxies and their black holes single organisms, two parts of a greater whole. The evidence leans toward yes. From their synchronized growth to their feedback loops, their relationship transcends mere proximity. It's a co-evolution forged over cosmic time. And if that's true, then every star, every planet, every one of us exists under the watchful pull of these dark giants, their invisible hands guiding the galaxy's fate as surely as mitochondria guide ours. The universe, it seems, has a knack for repeating its most successful designs, whether in the swirl of a cell or the spin of a galaxy. The Higgs field isn't just an abstract concept, it's the invisible fabric that makes reality tangible. Picture an ocean where every particle swims, some gliding effortlessly like photons, others trudging through like electrons weighed down by their own mass. This cosmic molasses doesn't just fill space, it interacts with every particle passing through it, granting substance to what would otherwise be ethereal wisps of energy. The closer a particle couples with this field, the heavier it becomes, as if the universe itself presses down with an unseen hand. Now imagine your own skin, the boundary that gives your body form, the surface where touch becomes possible. The Higgs field operates in eerily similar ways. Without it, atoms would zip through each other at light speed, never clumping into stars or planets. Your body would dissolve into a chaotic mist of weightless particles. Just as skin contains and defines you, the Higgs contains and defines the physical universe, turning raw energy into tangible matter. Scientists first confirmed this field's existence in 2012 at CERN Large Hadron Collider, where they observed the Higgs boson, a ripple in the field, like the splash when a pebble drops into water. But here's what's truly mind-bending. The Higgs field didn't activate until the universe was a trillionth of a second old. Before that critical moment, all particles moved masslessly through a symmetrical void. When the field switched on during cosmic inflation, it broke that symmetry, instantly giving weight to certain particles while leaving others untouched. This single event made chemistry possible, then biology, then consciousness. You're literally reading these words because the Higgs field chose its current strength over another. Some theorists take the skin analogy even further. Just as your skin regulates temperature and blocks pathogens, the Higgs might serve as a cosmic immune barrier. Calculations suggest its specific value, 125 billion electron volts, is improbably perfect. If it were slightly stronger, atoms would collapse; slightly weaker, they'd never form. This fine-tuning has led to wild speculation. Could the Higgs field be actively maintained, like a membrane under tension? Some versions of string theory propose it's anchored by higher dimensional branes, structures we can't perceive but that might prevent the field from destabilizing. Yet the Higgs isn't just a passive backdrop, it's dynamic, fluctuating. Quantum physics shows virtual particles constantly popping in and out of existence within it, like goosebumps appearing on skin. During extreme events like black hole collisions, these fluctuations might briefly warp, altering mass properties in ways we're only beginning to model. There's even speculation that dark matter interacts with a separate, hidden Higgs field, a kind of cosmic subcutaneous layer invisible to our current detectors. So is the universe truly skinned? The metaphor holds startling depth. Both skin and the Higgs define boundaries between self and environment. Both filter what passes through, your skin blocking UV rays while permitting vitamin D synthesis, the Higgs granting mass to quarks while letting photons race freely. Most importantly, both exist at the threshold of identity, the place where you end and the world begins. The Higgs field might be the ultimate example of nature's frugality, repurposing the same organizational principles from human biology to galactic structure. This realization flips our perspective. We usually think of particles as fundamental and space as the stage, but the Higgs suggests space itself is active, participatory, a medium that sculpts reality through interaction. You're not just in the universe, you're of it, shaped by its hidden architecture at every moment. And that means every time you feel the weight of a book in your hands or the ground beneath your feet, you're sensing the universe's defining membrane, the silent, omnipresent field that makes existence something rather than nothing. Neutrinos are the universe's ultimate shape-shifters, particles so elusive they can pass through a light year of lead without a single collision. But their real magic lies in their ability to transform mid-flight, switching between three distinct identities like a cosmic chameleon. One moment they're electron neutrinos, the next they're muon or tau neutrinos, oscillating between flavors as unpredictably as a teenager's moods. This isn't just quantum weirdness, it's a fundamental quirk that might hold the key to how the cosmos evolves, mirroring the way hormones orchestrate growth and change in living organisms. Picture a neutrino born in the sun's core, a tiny, nearly massless particle racing toward Earth at near light speed. By the time it reaches us, 8 minutes later, it might have morphed twice, like a character in a myth changing disguises. These oscillations aren't random. They're governed by precise quantum mechanics, a delicate interplay of mass and energy that makes neutrinos the universe's most enigmatic regulators. Just as hormones in your body like cortisol or adrenaline trigger cascades of change with minuscule concentrations, neutrinos influence cosmic structures despite their ghostly nature. The parallels grow eerie when you examine their impact. During a supernova, neutrinos carry away 99% of the dying star's energy, seeding the surrounding space with particles that might determine how future stars and planets form. Some theories suggest neutrino oscillations even tilted the balance between matter and antimatter in the early universe, explaining why we exist at all. Without these subtle shifts, the cosmos might have annihilated itself in a burst of pure energy, leaving nothing behind. But here's the twist: neutrinos don't just change themselves, they might reshape reality around them. In the primordial universe, their oscillations could have created density fluctuations that became the seeds for galaxies. It's as if these particles scribbled faint blueprints into the fabric of spacetime, guiding where cosmic structures would rise billions of years later. Modern detectors like Japan's Supermassive and have caught neutrinos mid-oscillation, their transformations betraying secrets about mass hierarchies that even the Large Hadron Collider can't probe. So are neutrinos the universe's hormonal messengers. The analogy holds surprising weight. Hormones operate at vanishingly low concentrations, yet they dictate growth, metabolism, and even behavior. Neutrinos, equally subtle, might steer the universe's development through their oscillations, quietly tweaking the rules of particle physics, nudging galaxies into being, even influencing the dark matter halos that bind the cosmos together. They're not just passive spectators, they're active participants in the grand narrative of existence. The deeper mystery lies in why they oscillate at all. Unlike other particles, neutrinos have masses so slight they defy the Standard Model's predictions. Some theorists propose they're tapping into hidden dimensions or interacting with undiscovered fields. Others speculate they might be Majorana particles, entities that are their own antiparticles, hinting at a symmetry so profound it could rewrite physics. Whatever the truth, neutrinos remind us that the universe thrives on transformation, from the smallest particles to the largest structures. Next time you feel the sun's warmth on your skin, remember, trillions of neutrinos are passing through you every second, flickering between identities like cosmic fireflies. They're silent, invisible, and utterly essential, the universe's way of whispering its secrets in a language we're only beginning to decode. And in their oscillations, we might just find the rhythm of creation itself. Dark energy isn't just pushing galaxies apart, it's revving up the cosmos like a cosmic adrenaline rush, accelerating the universe's expansion faster with each passing moment. Imagine you're in a car pressing the gas pedal, only to realize the pedal is sinking deeper on its own, hurtling you forward at speeds you never intended. That's the eerie reality of dark energy, an invisible force that makes up 68% of the universe's total energy, yet defies every attempt to explain its origin or ultimate purpose. Unlike gravity, which pulls matter together, dark energy operates like a survival mechanism, stretching space-time itself to keep cosmic structures from collapsing inward. It's as if the universe, faced with its own mortality, has kicked into a fight-or-flight response on a galactic scale. The discovery of dark energy came from a cosmic paradox. In the late 1990s, astronomers studying distant supernovae expected to find the universe's expansion slowing down due to gravity's pull. Instead, they found the opposite. Galaxies were fleeing faster than expected, as if some unseen hand had cranked up the dial on reality's engine. Subsequent measurements of the cosmic microwave background and large-scale galaxy distributions confirmed it. Dark energy wasn't just present, it was dominant, overriding gravity's tug with a repulsive force that grows stronger as space expands. The implications are staggering. If this acceleration continues, trillions of years from now, galaxies beyond our local group will vanish over the cosmological horizon, their light stretched beyond detectability. The universe, in essence, is isolating itself like a body diverting resources to its core during stress. But here's where the analogy gets unsettling. Adrenaline in your body spikes in response to immediate threats, then tapers off. Dark energy behaves differently. Observations suggest its density remains constant even as the universe grows, meaning its influence doesn't dilute with expansion. It's more like an endless infusion of stimulants, pushing the cosmos toward an unknown threshold. Some theorists speculate this could hint at a deeper intelligence in the universe's design, a failsafe against gravitational collapse. Others propose dark energy is a phase transition akin to water boiling into steam, where the vacuum of space itself is shifting into a new state, the most provocative theory. Dark energy might not be constant at all. Subtle anomalies in recent data suggest it could fluctuate over time, strengthening or weakening in response to cosmic conditions. If true, this would mean the universe isn't just expanding, it's reacting, adjusting its own growth rate like an organism regulating its metabolism. Imagine a scenario where dark energy surges during periods of intense star formation, as if the cosmos were making room for new creation, then eases during quieter epochs. Such behavior would blur the line between physics and biology, suggesting the universe doesn't just follow laws, it responds to them. What does this mean for us? If dark energy is the universe's adrenaline, then we're living in the middle of its rush, a brief window where galaxies are still close enough to see, and cosmic history hasn't been erased by expansion. But unlike a temporary human adrenaline spike, dark energy's effects are permanent. Every second, it's carving the future of reality, determining which structures will endure and which will fade into isolation. The universe, it seems, isn't just expanding, it's making choices. And in those choices, we might finally uncover whether it's merely a machine running on autopilot or something far more dynamic, a living, breathing entity fighting to shape its own destiny. Galaxies aren't just static islands in the void, some are cosmic nomads, cast adrift by gravitational forces to wander the intergalactic wilderness. Picture a herd of wildebeest forced from their grazing lands by drought, adapting to new terrain or perishing in the attempt. Now scale that up to galactic proportions. When galaxies get too close to the dense centers of their clusters, gravitational slingshots can eject them at staggering speeds, millions of miles per hour, sending them hurtling into the emptiness between clusters like celestial refugees. These runaway galaxies face a brutal journey, stripped of their gas by intergalactic winds, their star formation choked off as they drift into the cosmic equivalent of a desert. Take the galaxy known as Mirage's Ghost. Once part of a bustling cluster, it now streaks through the void at over 1,000 kilometers per second, its spiral arms stretched and distorted by the ordeal. Observations show its gas the raw material for new stars, being ripped away in a vast wake like breadcrumbs marking its path through the darkness. Yet against all odds, some of these galactic nomads survive. Just as animals migrating to new ecosystems evolve unique traits, ejected galaxies adapt. Their remaining gas clumps into dense knots, sparking bursts of star formation in isolated pockets, a desperate but ingenious strategy to keep the stellar fires burning. Here's where the analogy gets chilling. In nature, migration is often a response to overcrowding or scarcity, a way to prevent resource depletion. Could the same be true for galaxies? When too many crowd a cluster's core, gravitational interactions fling the excess outward, thinning the herd to maintain equilibrium. This isn't random chaos, it's a regulatory mechanism, a cosmic version of predator-prey dynamics where gravity plays the role of both hunter and habitat. But the real mystery lies in what happens next. Some ejected galaxies, like hypervelocity stars before them, may escape their clusters entirely, destined to drift forever in the void. Others, like the famous orphan galaxy NGC 4500, find themselves captured by new clusters, their trajectories rewritten by unseen gravitational tides. These cosmic adoptions mirror biological invasions, where introduced species reshape ecosystems. A wandering galaxy plunging into a new cluster can disrupt delicate gravitational balances, triggering chain reactions of collisions and mergers that remake entire galactic neighborhoods. So is this cosmic Darwinism. The parallels are undeniable. Just as natural selection favors traits suited to an environment, galaxies in clusters evolve differently from their nomadic cousins. Cluster galaxies grow fat on abundant gas, their stars aging in relative stability. Ejected galaxies, by contrast, become lean and efficient, their survival hinging on adaptability. Over billions of years, this gravitational winnowing may shape the distribution of galaxies as profoundly as evolution shaped Earth's biodiversity. The universe, it seems, has its own version of survival of the fittest, not played out in genes and ecosystems, but in gravity and star formation. Yet there's a twist. Unlike biological migrations, galactic exile isn't always a death sentence. Isolated galaxies, freed from the crowding and turbulence of clusters, sometimes become blue stragglers, late blooming marvels where star formation reignites against all odds. These lone wanderers remind us that the cosmos, like life, thrives on resilience. Whether in the Serengeti or the Virgo supercluster, the rule holds true: adapt or fade away. And in that relentless dance, we glimpse a universe that doesn't just arrange matter. It curates it, testing each galaxy's mettle against the unforgiving vastness of space. A supernova doesn't just die, it exhales. When a massive star reaches the end of its life, it doesn't fade quietly. It detonates with the energy of a billion suns, blasting its innards across light years in a fiery breath of iron, gold, and oxygen. These elements don't vanish into the void, they become the raw materials for new stars, planets, and eventually, life itself. It's a cosmic version of respiration, where the universe recycles stardust in an endless cycle of death and rebirth. Think of it like a forest fire, destructive in the moment but clearing space for new growth, its ashes fertilizing the soil of space. Now picture the Crab Nebula, the remnants of a supernova observed by astronomers in the year 1054. Today, its swirling tendrils stretch 11 light-years across, rich with sulfur, carbon, and neon elements forged in the star's final moments. These aren't just inert chemicals, they're the building blocks of future solar systems. Every heavy atom in your body, the calcium in your bones, the iron in your blood was once scattered by such an explosion, exhaled by a dying star billions of years ago. The universe doesn't waste, it breathes in chaos and breathes out creation. But here's what's truly remarkable: this process isn't random. Supernovae distribute elements unevenly, like a gardener planting seeds in fertile patches. Some regions of space become enriched with metals, as astronomers call elements heavier than hydrogen and helium, while others remain pristine. This unevenness shapes the evolution of galaxies, determining where gas clouds collapse into stars and where they linger as barren voids. It's a feedback loop as precise as your own breathing. Inhale oxygen, exhale carbon dioxide, sustaining the balance of life. In the cosmos, stars inhale hydrogen, exhale metals, and sustain the cycle of cosmic chemistry. Parallels run even deeper. Just as your lungs regulate oxygen flow to match your body's needs, supernovas self-regulate their impact. Too many explosions in a short time, and galaxies could over-enrich, choking on their own heavy elements. Too few, and new stars would lack the ingredients for rocky planets. Observations of distant galaxies show this balance in action. Regions with frequent supernovae develop metal-rich stars, while quieter areas remain primordial. The universe, it seems, has its own respiratory rhythm, a tempo set by the lives and deaths of its stellar inhabitants. Could this cycle be more than metaphorical? Some theorists propose that supernova feedback acts like a cosmic immune system, clearing out old material to make way for the new. Others see it as a form of galactic metabolism, converting simple elements into complex ones to fuel further growth. The math is startlingly similar. The energy released by a single supernova can trigger star formation in nearby gas clouds, much like a spark igniting tinder. Over billions of years, this process builds galaxies as intricately as your body builds cells layer by layer, breath by breath. So is the universe truly breathing? In the strictest sense, no, but the echoes are undeniable. From the explosive death of stars to the gentle drift of enriched gas through spiral arms, the cosmos moves in cycles of expulsion and absorption, decay, and renewal. And in those cycles, we find ourselves not just observers of the universe's grand rhythm, but products of it. Every atom in your hands, your eyes, your thoughts, was once part of a star's final exhale. You are quite literally the universe remembering how to breathe. Cosmic strings aren't just theoretical oddities. They could be the universe's hidden scaffolding, stretching across space-time like invisible tendons holding reality together. Picture the fibrous strands of collagen in your own body, giving structure to skin and muscle. Now imagine filaments of pure energy, thinner than a proton but stretching billions of light years, woven through the cosmos since the first moments after the Big Bang. These aren't mere wrinkles in space-time. They're defects frozen into existence when the laws of physics underwent their first violent phase transitions, like cracks forming in ice as water freezes. And just as tendons transmit force between bones, cosmic strings might channel gravitational energy across the universe, shaping everything from galaxy clusters to the voids between them. The math behind these bizarre structures is shockingly elegant. Unlike black holes or neutron stars, cosmic strings would lack ends. They'd either form infinite lines or loop back on themselves like cosmic lassos. Their gravitational influence wouldn't come from mass but from tension, warping space-time around them like a guitar string bends the air with its vibrations. A single string just 6 miles long could contain more energy than the sun emits in a billion years, yet it would weigh almost nothing. That tension could explain some of the universe's most puzzling features, like the way certain galaxy clusters align in vast, unexplained arcs across the sky, as if threaded onto invisible strings. But here's where it gets stranger. These cosmic tendons might not just structure space, they could actively shape time. Simulations suggest moving cosmic strings could create closed time-like curves, regions where time loops back on itself. It's a concept straight out of science fiction, but the physics is sound. The immense tension in a vibrating string could twist space-time enough to bend the arrow of time into a circle. While we've yet to detect one directly, astronomers have searched for their signatures in the cosmic microwave background, looking for telltale temperature fluctuations or double images of distant quasars split by a string's gravitational lensing. The most tantalizing possibility, cosmic strings might be the universe's repair mechanism. When two strings cross, they could reconnect in a process called intercommutation, releasing bursts of gravitational waves, ripples in space-time detectable by observatories like LIGO. Some theories even suggest these events could seed primordial black holes or ignite star formation in their wake, acting as cosmic catalysts for new structures. In this way, strings wouldn't just support the universe, they'd actively participate in its evolution, like tendons that don't just stabilize a joint but help it grow stronger under stress. So are these filaments the universe's connective tissue? The analogy holds remarkable depth. Tendons adapt to stress by thickening where tension is greatest. Cosmic strings may similarly concentrate near galaxy clusters, their gravitational influence reinforcing the densest regions of the cosmos. They'd also share a tendon's silent efficiency operating behind the scenes, unnoticed until they falter. A snapping cosmic string, though unimaginably rare, could release enough energy to briefly outshine an entire galaxy, a reminder of the hidden forces binding reality together. Whether they exist or not, cosmic strings challenge our perception of the universe as a passive arena. Instead, they paint a picture of space-time as dynamic architecture, crisscrossed with energy cables that might be the framework upon which everything else hangs. And if we ever detect one, it won't just confirm a wild theory. It'll reveal the universe as a place where even emptiness has structure, where the void itself is threaded with invisible tendons, flexing and resonating to the rhythm of cosmic expansion. What if our universe isn't alone but just one leaf in an infinite cosmic forest? Multiverse theory suggests reality might be a vast ecosystem of parallel universes, each with its own laws of physics, constants, and even versions of you. But here's the twist: these universes might not exist in isolation. Like species in a rainforest, they could interact, compete, and even depend on one another in ways that redefine what it means to be alive on the grandest scale. Picture a coral reef teeming with life. Each organism occupies its niche, yet all are connected through invisible threads: predation, symbiosis, the flow of nutrients. Now replace coral with universes. Some theories propose that bubble universes collide in higher dimensional space, exchanging energy or information like trees sharing resources through fungal networks. Others suggest black holes might be cosmic wormholes, birthing new universes in their depths like seeds sprouting from fruit. The math behind eternal inflation, a leading multiverse model, shows universes budding off endlessly, some thriving with stable physics, others collapsing instantly, a Darwinian selection playing out across cosmic time. The evidence is speculative but haunting. Tiny anomalies in the cosmic microwave background, the afterglow of the Big Bang, hint at bruises where our universe might have bumped into a neighbor. Quantum mechanics, with its probabilities and parallel states, feels almost designed for a multiverse, as if every choice spawns a new branch in an ever-growing tree. Even the fine-tuning problem, the inexplicably perfect balance of physical constants enabling life, makes sudden sense if countless universes exist, each a roll of the dice. We're here not because the cosmos favored us, but because we won the ultimate lottery, a universe where physics allows stars, planets, and minds to form. But what if the connections run deeper? Some models propose universes feed off one another. Imagine a young universe drawing energy from an older one through quantum entanglement, like a sapling tapping into a mycorrhizal network. Or consider the holographic principle, where our three-dimensional reality is a projection of information stored on a distant boundary, a cosmic version of how your DNA encodes an entire body in two strands. If true, universes might share data the way organs share hormones, synchronizing in ways we can't yet perceive. The implications are staggering. If universes interact, they could form a self-regulating meta-organism, balancing birth and decay across dimensions. A dying universe might trigger the birth of another, recycling energy like fallen leaves, nourishing new growth. Civilizations in one universe could consciously or not influence another's development, their gravity rippling through higher dimensions like whale song echoing through ocean depths. So where does that leave us? If the multiverse is a living network, then humanity isn't just a speck in one universe. We're threads in a tapestry woven across existence itself. Every discovery we make, every star we map, might resonate in ways we can't yet imagine. The night sky isn't a ceiling, it's a window, and beyond it, an ecosystem of realities pulses with possibilities we're only beginning to glimpse. Plasma isn't just the stuff of stars, it might be the universe's most prolific life form. Picture a petri dish teeming with bacteria, their colonies pulsing and dividing. Now imagine that same activity unfolding in the vast stretches of space, where superheated plasma-charged particles so energetic they've shed their electrons, twists into filaments, spirals, and even self-replicating structures. These aren't just random swirls of gas, they're dynamic, organized systems that eerily mimic the behavior of living cells. Scientists call them plasmoids, and their uncanny resemblance to microorganisms has sparked a radical question. Could the universe be crawling with primitive plasma-based life, invisible to our eyes but thriving in the searing heat of nebulas or the magnetic fields around black holes? Take the work of physicist David Bohm, who observed plasma forming double-layer barriers that act like cell membranes, separating internal and external environments. These layers don't just sit there, they pulse, merge, and even communicate through electromagnetic waves, creating feedback loops reminiscent of neural networks. In lab experiments, plasma has been coaxed into forming helix structures akin to DNA, while natural phenomena like ball lightning, a mysterious, glowing orb of plasma that dances unpredictably, behaves with a spontaneity that feels almost biological. The more we study plasma, the more it defies the line between chemistry and something far stranger. But here's where it gets provocative. Some theorists, like Nobel laureate Hans Alfvén, proposed that plasma could exhibit lifelike properties on cosmic scales. In the ionized soup of stellar nurseries or the magnetospheres of planets, plasmoids might compete for resources, evolve in complexity, or even exhibit primitive forms of selection. Imagine a star's corona not just as a chaotic inferno, but as a dynamic ecosystem where plasma structures feed on magnetic energy, replicate through instability-driven splitting, and die when their energy dissipates. It's a vision of life stripped down to its essentials, not carbon and water, but charged particles and forces. Critics argue this is just poetic analogy, that self-organization doesn't equal life. Yet the parallels are hard to ignore. Like bacteria, plasmoids respond to their environment, maintain boundaries, and harness energy to sustain their structure. The dusty plasma experiments of physicist Vadim Taitovich even showed microscopic particles in plasma arranging themselves into helical chains that twist, divide, and transfer charge in ways eerily reminiscent of microbial reproduction. If life is fundamentally about information processing and adaptation, then plasma's ability to form, store, and transmit patterns of electromagnetic energy starts to feel less like physics and more like protobiology. So is plasma the universe's microbiome? The answer might depend on how we define life. On Earth, life requires liquid water and organic molecules. But in the scorching hearts of stars or the frigid voids between galaxies, plasma could be following a different playbook, one written in magnetic fields and particle collisions rather than DNA. Whether these structures truly qualify as alive or not, they force us to confront a humbling possibility, that life as we know it might just be one narrow expression of a far broader cosmic phenomenon. The universe doesn't just harbor life, it might be alive in ways we're only beginning to imagine, its true complexity hidden in the shimmering, electrified dance of its most abundant substance. Gravitational waves don't just ripple through space-time, they throb with the rhythm of cosmic life. When two black holes spiral toward collision, they don't crash silently. They ring the fabric of reality like a bell, sending out waves that pulse at frequencies so precise, scientists can translate them into sound. The result: a deep, resonant whoop that rises in pitch before ending abruptly, a gravitational heartbeat echoing across billions of light years. These waves aren't just noise, they're the universe's vital signs, carrying secrets about its health, its age, and even its hidden structure. Take the first gravitational waves ever detected, labeled GW150914. Born from the merger of two black holes 36 and 29 times the mass of our Sun, their collision released more energy in a fraction of a second than all the stars in the observable universe combined. But it's the pattern of those waves that's truly mesmerizing. As the black holes orbited faster and closer, their gravitational waves increased in frequency, just like an accelerating heartbeat before climax. When they finally merged, the resulting black hole rang down with quieter aftershocks, a phenomenon called quasi-normal modes, which physicists compare to a struck bell's fading hum. Here's where it gets eerie. These gravitational waveforms match the same mathematical curves that describe heartbeats in electrocardiograms. The rise and fall of a black hole merger's frequency mirrors the peaks and valleys of a human EKG so closely that you could overlay the two graphs and see the resemblance. It's as if the universe and biology share a hidden language of rhythm, where the pulse of a star-sized collision and the thrum of a human ventricle follow the same universal score. But these cosmic heartbeats do more than just fascinate, they diagnose. Just as doctors infer heart health from EKG readings, astrophysicists extract the universe's secrets from gravitational waves. The frequency of a merger reveals the black hole's masses, the waveform's shape betrays their spins, the aftershocks hint at the new black hole's stability. Some researchers even speculate that gravitational waves from the earliest moments after the Big Bang might still reverberate today, a faint background hum akin to a cosmic fetal heartbeat, evidence of the universe's fiery birth. The parallels go deeper. Your heartbeat adapts to stress, speeding up or slowing down based on your body's needs. Black holes do something similar. In dense galactic environments, they merge more frequently, their gravitational wave pulse quickening like a heart under exertion. Isolated black holes, by contrast, might go billions of years without a merger, their rhythms slow and steady. This isn't just analogy, it's a window into how the universe self-regulates, balancing chaos and order through these invisible tremors. So are we eavesdropping on the universe's circulatory system, with detectors like LIGO and Virgo now catching gravitational waves weekly? The answer leans toward yes. Each collision is a systolic surge in the cosmic bloodstream, each ripple a whisper about how mass and energy flow through the grandest scales. And just as stethoscopes once revolutionized medicine, gravitational wave astronomy is rewriting our understanding of the cosmos, not as a static void, but as a living, breathing entity whose pulse we're finally learning to hear. Vacuum decay sounds like science fiction, but it might be the universe's ultimate expiration date, a cosmic self-destruct sequence written into the fabric of reality itself. Picture a single cell in your body recognizing it's beyond repair and triggering apoptosis, a controlled death that protects the larger organism, now scaled at up to universal proportions. According to quantum field theory, our universe might exist in a false vacuum, a temporary state of stability that could, at any moment, collapse into a true vacuum with entirely different physical laws. If this happens, a bubble of destruction would expand at light speed, rewriting physics as it goes, erasing stars, planets, and even space-time itself in an irreversible wave of annihilation. The chilling part, we wouldn't see it coming until it was too late. This isn't just theoretical doom-mongering. The math checks out. In the 1970s, physicist Sidney Coleman calculated how quantum fluctuations could puncture the false vacuum, creating a nucleation point, like a tiny crack in a frozen lake that spreads uncontrollably. Once initiated, the collapse would be unstoppable, transforming the universe into something unrecognizable. The parallels to cellular apoptosis are unnerving. Both processes serve as reset buttons. Apoptosis clears damaged cells to preserve tissue health, while vacuum decay might clear a universe with unstable physics to make way for, well, we don't know what. Some theories suggest a new universe with different constants could emerge from the wreckage, like a phoenix rising from ashes. But here's the twist: vacuum decay isn't necessarily doom. It could be cosmic evolution. Just as apoptosis removes dysfunctional cells to maintain an organism's health, vacuum decay might be the universe's way of pruning flawed configurations, allowing more stable realities to dominate. The anthropic principle even suggests we exist in a universe that hasn't decayed precisely because we're here to observe it, implying most other configurations have already collapsed. In this view, our universe isn't immortal, it's just lucky. The real mystery lies in the trigger. What would push the false vacuum over the edge? Some models point to high-energy particle collisions, like those in the Large Hadron Collider, though the probabilities are vanishingly small. Others speculate that quantum tunneling, a particle spontaneously jumping to a lower energy state, could set it off randomly, anywhere, anytime. There's even a hypothesis that vacuum decay has already happened elsewhere in the cosmos, and its lethal bubble is racing toward us right now, undetectable until it arrives. So is the universe mortal? The answer might be yes, but not in the way we traditionally conceive death. It's not aging or running out of energy. It's a built-in expiration clause, a subroutine in reality's code. And that changes everything. If the cosmos can self-terminate, then we're not just passengers in a stable, eternal universe. We're temporary residents in a dynamic, precarious system, one that could reboot itself at any moment. The irony, this existential fragility, is what makes our existence so astonishing. Every second we observe the universe, we're witnessing a cosmic tightrope walk, a reality balanced precariously between being and oblivion. The Great Attractor doesn't just tug at galaxies, it thinks them into motion. Hidden behind the Milky Way's dusty veil, this gravitational behemoth exerts a pull so powerful it's dragging hundreds of thousands of galaxies, including our own, toward it at 14 million miles per hour. But here's what defies explanation. The Great Attractor isn't just a cluster of mass. It's an anomaly, a cosmic command center whose influence stretches far beyond what visible matter should allow. Some theorists whisper it might be more than a gravitational oddity. It could be evidence of a universal will, a focal point where the cosmos itself exerts intention. Picture the human brain for a moment. When you decide to move your arm, neurons fire in precise sequences, their electrical impulses cascading down your spinal cord. Now imagine galaxies as limbs of a vast cosmic body, their trajectories not random but directed, as if responding to some unseen neural command. The Great Attractor's pull isn't uniform like a black hole's grasp, it's selective, almost strategic. Galaxies flow toward it along filaments of dark matter, like signals racing along axons. Could this be the universe's version of a motor cortex, coordinating movement on a scale we can barely comprehend? The numbers deepen the mystery. Based on visible matter alone, the Great Attractor's mass shouldn't generate such immense pull. Yet something, perhaps vast reservoirs of dark matter, or something even stranger, is bending space-time like a thought bending reality. In the 1980s, astronomers discovered entire galaxy clusters, like the Norma cluster, falling into this region like iron filings to a magnet. But the attractor itself remains shrouded, its core obscured by our own galaxy's bulk. It's as if the universe placed a blindfold over our eyes, forcing us to sense its presence indirectly through the motion of everything around us. This isn't just gravity, it's gravity with a pattern. The galaxies flowing toward the Great Attractor aren't moving chaotically. They're aligning, their paths converging like tributaries into a river. Some researchers compare it to ant colonies, where individual ants follow simple rules that collectively create intelligent behavior. Could the attractor be a cosmic emergent phenomenon, a thought arising from the universe's underlying structure? The idea isn't as far-fetched as it sounds. In simulations, dark matter's gravitational web naturally forms nodes where flows concentrate, creating focal points that resemble uncannily neurons in a neural network. Yet the most provocative theory comes from those who see consciousness as fundamental to reality. If the universe is, in some sense, aware, then the great attractor might be less a place and more a process, a gravitational manifestation of cosmic intent. Philosophers like Alfred North Whitehead argued reality is built from moments of experience, not inert matter. In that light, the attractor becomes less a thing and more an act, the universe deciding to gather itself together. Of course, mainstream cosmology favors tamer explanations, unseen mass, exotic physics, or even larger structures beyond the attractor itself, but the parallels linger, unsettling and profound. Whether it's a flaw in our understanding of gravity or a glimpse of something deeper, the great attractor challenges us to reconsider not just how the universe moves, but why. Every galaxy drifting toward it is a clue in a mystery we've only begun to unravel, one that might ultimately reveal whether the cosmos is a machine, a mind, or something far stranger. At the smallest scales imaginable, space-time isn't smooth, it seethes. Quantum foam, the turbulent foundation of reality, churns like a microscopic ocean in a storm, its energy bubbling into fleeting particles that pop in and out of existence too quickly to measure. This isn't just empty space, it's a seething, dynamic medium where the very fabric of the universe behaves less like a static stage and more like the cytoplasm inside a living cell, constantly reorganizing itself in bursts of chaotic creativity. Picture a single-celled organism under a microscope, its interior bustling with vesicles, proteins, and strands of DNA colliding in a dance of chemical activity. Now zoom in on spacetime itself, past atoms, past quarks, down to the Planck scale. Here, the vacuum isn't empty. It's a frothing sea of virtual particles, pairs of matter and antimatter that borrow energy from nowhere, exist for a fleeting instant, then annihilate each other in a flash of perfect balance. This ceaseless activity mirrors the metabolic processes of a cell, where molecules form and break apart in precise, rhythmic cycles. The universe, it seems, is never truly at rest. Even in its quietest corners, it thrums with latent potential. But here's where the analogy gets spine-tingling. Just as cellular division creates new life from existing material, quantum foam might be the nursery for reality itself. Theories like loop quantum gravity suggest spacetime isn't continuous but granular, composed of tiny, indivisible units. Think of them as cosmic pixels. These atoms of space could fluctuate, merge, or split in ways eerily reminiscent of mitosis, the process by which cells replicate. Some models even propose that the birth of virtual particles in the quantum foam isn't random but follows hidden patterns, like the regulated divisions of stem cells in an embryo. The implications are staggering. If spacetime shares structural and dynamic qualities with living tissue, does that mean the universe grows and heals like an organism? Observations of cosmic voids, massive, empty regions where galaxies are mysteriously scarce, hint at this possibility. These voids might be the scars of quantum fluctuations frozen in time, patches where spacetime's cellular repair mechanisms failed to fully normalize. Meanwhile, regions rich with galaxies could represent zones where the quantum foam's activity aligned just right, fostering complexity much like fertile soil nurtures life. Of course, not all physicists embrace this biological lens. Critics argue that quantum foam is purely mathematical, a placeholder for unknowns rather than evidence of cosmic life. Yet the parallels persist. When particles tunnel through barriers they shouldn't be able to cross, it recalls the way enzymes navigate cellular membranes with improbable precision. The entanglement of particles across vast distances mirrors the instantaneous communication between proteins in a signaling pathway. Even the holographic principle, the idea that our three-dimensional reality might be encoded on a two-dimensional surface, echoes how Decay's linear code unfolds into a living, breathing organism. So is the universe alive? Quantum foam doesn't offer a definitive answer, but it blurs the line between physics and biology in ways that challenge our definitions. From the fractal branching of galaxies to the pulse of gravitational waves, reality seems obsessed with recycling the same blueprints across scales. And if the foundation of existence shares rhythms with the processes that animate us, it raises a humbling possibility. We're not just observers of the cosmos. We're expressions of it, temporary eddies in a quantum sea that's far more dynamic and perhaps far more familiar than we ever dared to dream. Baryon asymmetry isn't just a quirk of physics, it's the universe's most consequential imbalance, a fundamental preference that shaped everything from galaxies to your own body. Picture a cosmic coin toss at the dawn of time. Matter and antimatter should have been created in equal amounts, annihilating each other instantly and leaving behind nothing but pure energy. Yet here we are, in a universe where matter dominates so completely that antimatter is rarer than gold. This isn't just statistical noise, it's a lopsidedness so extreme it borders on personality, as if the cosmos itself has a type. Take the humble electron. For every one that exists, there should be a positron, its antimatter twin with identical mass but opposite charge. When they meet, they vanish in a flash of gamma rays. Yet somehow, for every billion matter-antimatter pairs created in the early universe, one extra matter particle survived. That tiny excess, just one part in a billion, became the raw material for every star, planet, and living thing. The question isn't just how this happened, but why. Does this skew reveal something deeper about the universe's identity? Like sexual dimorphism in species where males and females evolve distinct traits. The parallels are unnerving. In biology, dimorphism arises from evolutionary pressures, think peacock's tails or lion's manes. Could baryon asymmetry be the universe's version of selective pressure, a bias baked into physical laws that made complexity possible? Experiments at CERN LHC have caught particles called mesons decaying slightly more often into matter than antimatter, violating what physicists call CP symmetry. It's as if the universe has a subtle but insistent preference, like a sculptor favoring one hand over the other. Some theorists push the analogy further. If matter is the universe's masculine or feminine side, terms used purely metaphorically, then its dominance might not be accidental. Certain grand unified theories suggest antimatter could have been exiled to hidden regions of the cosmos or even alternate dimensions, leaving our observable universe as one half of a grand duality. Others propose that antimatter behaves differently under gravity, subtly sinking into the fabric of space-time like cosmic dark matter. The implications are staggering. Without this asymmetry, reality would be sterile, a featureless void with no structures, no chemistry, no life. In that sense, baryon asymmetry isn't just a curiosity. It's the universe's reproductive strategy, a necessary tilt toward fertility. And just as sexual reproduction drives genetic diversity, matter's excess might fuel cosmic evolution, allowing galaxies to cluster, stars to ignite, and planets to coalesce. So does the universe have a sex, not in any literal sense, but the echoes are undeniable. From the pairing of particles to the generative imbalance that birthed galaxies, the cosmos seems obsessed with duality, preference, and the creative tension between opposites. Whether it's yin and yang or matter and antimatter, the universe thrives on asymmetry, and in that lopsidedness, we find ourselves, the unlikely heirs of a cosmic bias written into the first seconds of time. Neutron stars aren't just stellar corpses, they're cosmic shape-shifters, teetering on the knife's edge between existence and oblivion. Born from the explosive deaths of massive stars, these city-sized objects pack more mass than our Sun into a sphere so dense a single teaspoon would weigh 1 billion tons. But their true magic lies in their potential. Like stem cells in an embryo, neutron stars hold the latent capacity to become something entirely different. A pulsar flashing like a lighthouse, a magnetar with a magnetic field strong enough to erase credit cards from 1,000 miles away, or if enough mass accumulates, a black hole, the universe's ultimate endpoint. This transformative ability makes them more than relics. They're the cosmos's way of keeping its options open, a reminder that even in death, stars harbor the seeds of rebirth. Consider the case of Swift J 1845.07, a neutron star caught in the act of morphing. In 2017, astronomers watched as it devoured gas from a companion star, its gravity compressing the material until it briefly tipped the scales toward black hole territory. Then, just as suddenly, it ejected a fraction of that mass in a violent jet, pulling back from the brink. This delicate dance, hovering near a critical threshold without fully crossing it, mirrors how stem cells maintain pluripotency, resisting specialization until the right conditions emerge. The universe, it seems, has its own version of cellular hesitation, a pause before commitment that allows for infinite possibility. The parallels run deeper. Just as stem cells differentiate based on chemical signals in their environment, neutron stars evolve according to the physics of their surroundings. Isolated neutron stars often become pulsars, their precise rotations slicing the darkness with beams of radiation. Those born in binary systems might accrete material, their surfaces erupting in thermonuclear explosions called X-ray bursts. And in rare cases, like the infamous magnetar SGR 1806-20, they unleash starquakes so powerful they briefly outshine every other object in the Milky Way. Each path reflects the universe's improvisation, a response to local conditions that transforms raw potential into cosmic function. But here's the most tantalizing possibility. Neutron stars might not just become black holes, they could birth new universes. Some theories suggest the extreme conditions inside a collapsing neutron star could trigger a quantum tunneling event, creating a baby universe in its core. This speculative idea, dubbed universal natural selection, posits that our own cosmos might have begun this way, spawned inside the hyper-compressed heart of a star from another reality. If true, neutron stars wouldn't just be regenerating matter, they'd be regenerating existence itself, spinning off new cosmic lineages like stem cells dividing into specialized tissues. So are neutron stars the universe's regenerative agents? The evidence leans toward yes. From their ability to repurpose stellar debris into new forms to their role as potential gateways to other realities, they embody the cosmos's restless creativity. Every time one pulses, quakes, or collapses, it's not just a dead star acting out, it's the universe experimenting, testing the boundaries of what's possible. And in that endless trial and error, we find the same principle that governs life: adaptation, transformation, and the stubborn refusal to let entropy have the final word. Olber's paradox poses a simple question with cosmic implications. Why is the night sky dark? If the universe is infinite and filled with stars, every line of sight should eventually land on a star's surface, making the night sky blaze as bright as the sun. Yet it doesn't, and that absence of light speaks volumes. The darkness isn't just empty space. It's a clue that the universe operates like a living system, regulating its own vision, like an iris dilating to control how much light reaches the retina. Think of your own eyes adjusting to a darkened room. Pupils expand to capture every available photon, but there's a limit: too little light, and the world fades to black. The cosmos behaves similarly. Distant starlight gets absorbed by interstellar dust or stretched into invisibility by the expansion of space, a phenomenon called redshift. But here's the twist: these aren't just passive filters. They're dynamic processes that selectively gate how much of the universe's own radiance reaches any given point. It's as if space-time itself has a kind of sensory feedback loop, tuning its transparency like a lens adjusting its focus. The paradox takes on new depth when you consider the cosmic microwave background, the faint afterglow of the Big Bang. This uniform glow is often called the universe's baby picture, but it's also a kind of perceptual boundary. Just as your optic nerve translates light into electrochemical signals, the CMB encodes the universe's earliest observable state, a snapshot of reality's limits. Beyond it lies an era so dense with energy that light couldn't travel freely, a cosmic blind spot where the universe was, in a sense, too bright to see itself. This selective visibility mirrors biological vision in eerie ways. Your brain doesn't process every photon that hits your retina. It discards redundant signals, enhances contrasts, and even fills in gaps to construct a coherent image. The universe might be doing something similar. Galaxies cluster along filaments of dark matter, leaving vast voids between them, a structure that ensures light arrives in patterns, not a uniform glare. Even the finite speed of light acts as a filter, ensuring we only perceive stars whose photons have had time to reach us, like neural delays that sync perception with the present moment. Could this imply a universe that sees, not in the way we understand sight, but perhaps in a deeper structural sense? Just as a spider senses vibrations through its web, the cosmos might know its own structure through the propagation of light and gravity. When a supernova explodes, its light ripples across galaxies, carrying information about the intervening space. Black holes warp spacetime so severely that they act like cosmic lenses, bending light around them in predictable arcs. These aren't just physical phenomena, they're the universe's way of mapping itself, a feedback system where energy and information circulate like nerve impulses. The most profound implication lies in the paradox's resolution. The darkness of the night sky isn't a flaw, it's a feature. Without it, the universe would be a blinding, featureless sea of light, incapable of fostering complexity. The same mechanisms that dim distant starlight also allow planets to cool, molecules to form, and life to emerge. In that sense, Olber's paradox isn't just about missing light. It's about the universe curating its own perception, creating pockets of shadow where something new can grow. The night sky isn't empty, it's a canvas, and the darkness is where the cosmos paints its future. Panspermia turns the cosmos into the ultimate matchmaker, a celestial dance where life's building blocks hitch rides on comets, asteroids, and interstellar dust like microscopic stowaways. Imagine a dandelion releasing its seeds into the wind, except here, the wind is the solar wind, and the seeds are amino acids or even hardy microbes buried deep within icy space rocks. When these wanderers crash into planets with the right conditions, like Earth 4 billion years ago, they might just jumpstart biology itself. This isn't just sci-fi speculation. Meteorites like the Murchison meteorite, which landed in Australia in 1969, were found packed with over 90 different amino acids, including some not present on Earth. It's as if the universe delivered a pre-packaged starter kit for life, addressed to whom it may concern, but Panspermia goes further than just seeding ingredients. Some extremophiles, Earth's toughest microorganisms, can survive the vacuum of space, extreme radiation, and scorching re-entry temperatures. Tardigrades, those microscopic water bears, have even been experimentally exposed to open space and revived unharmed. If life can endure such conditions, why couldn't it traverse the galaxy, hibernating in the icy belly of a comet until it finds a hospitable new world? The math is tantalizing, given the trillions of comets ejected during our solar system's chaotic youth and the billions of years they've had to wander. The odds that at least one carried life spark aren't just plausible, they're statistically likely. Here's where the theory gets provocative. If life spread this way, then Earth might not be its only outpost or even its origin. Mars, with its ancient river valleys and subsurface lakes, could have once harbored microbes that hitched a ride to Earth aboard debris blasted into space by asteroid impacts. Europa's hidden ocean or Enceladus's geysers might shelter life descended from the same cosmic ancestry. In this view, the universe isn't just a sterile stage for life. It's a vast reproductive network, with comets as its pollinators and planets as its fertile soil. The implications rewrite our place in the cosmos. If life hops between worlds, then we and every blade of grass, every hummingbird, every bacterium might be descendants of interstellar travelers. Our DNA could carry echoes of a lineage that began light years away, making us less Earthlings and more universalings. Some researchers take it further, suggesting that Panspermia isn't accidental but inevitable, a natural phase in planetary evolution, like spores ensuring a species' survival by dispersing. The universe, in this light, doesn't just allow life, it cultivates it, scattering blueprints wherever conditions allow. Yet Panspermia isn't without its skeptics. Critics argue that even if life's ingredients are universal, the leap from amino acids to a living cell remains astronomically complex. Others point out that radiation in space would shred unprotected DNA over long journeys. But counterarguments abound. Perhaps life's precursors, not fully formed organisms, made the trip, or maybe protective minerals shielded them en route. The debate isn't just academic, it fuels missions like NASA OSIRIS-REx, which returned samples from asteroid Bennu, and ESA's Rosetta, which landed on a comet, hunting for clues to life's cosmic commute. So are we the universe's children? Panspermia suggests a humbling truth. Life might not belong to any one planet. It could be a shared inheritance, a thread connecting every habitable world in the galaxy. From the icy plumes of Enceladus to the methane lakes of Titan, the cosmos whispers the same question. If life could travel here, where else might it have gone? The answer could rewrite not just our origins, but our destiny, as passengers on a cosmic ark, sailing the stellar winds toward an endless horizon of possibilities. Entropic gravity flips everything we thought we knew about the universe's most familiar force. Forget Newton's apple or Einstein's warped spacetime. This radical theory suggests gravity isn't a fundamental force at all, but a side effect of cosmic aging, a shadow cast by the universe's slow march toward disorder. Picture an old photograph left in the sun. As it yellows and cracks over time, patterns emerge that weren't there originally. Entropic gravity proposes that what we call gravity might be those very wrinkles, the universe's way of keeping track of its own decay. The math behind this is as elegant as it is unsettling. Physicist Eric Verland's formulation treats gravity as an emergent property, like how the wetness of water isn't inherent to individual molecules but appears when trillions interact. In this view, every galaxy, every planet, even the pull you feel when you drop your phone, stems from microscopic quantum bits embedded in spacetime's fabric, adjusting to increasing entropy, nature's tendency toward chaos. The more disorder accumulates, the more space remembers its history, creating what we perceive as gravitational attraction. It's as if the universe has a built-in hourglass, and gravity is the sand trickling down. Black holes become the ultimate test case for this theory. Under entropic gravity, these cosmic voids aren't just collapsed stars but entropy accelerators, regions where disorder skyrockets so intensely that space-time itself knots up. They're event horizons. That's where information gets scrambled beyond recovery, like shredding documents to maximize chaos. The eerie glow of Hawking radiation around black holes fits perfectly. It's the universe's way of balancing entropy's books, leaking energy to maintain equilibrium. If entropy is the universe's aging process, then black holes are its liver spots, concentrated patches where time's wear and tear becomes visible. But here's where it gets prophetic. If gravity truly ties to entropy, then the accelerating expansion of the universe driven by dark energy might not be a mystery at all. Just as an aging tree's bark cracks wider with time, the cosmos could be stretching itself thin to accommodate mounting disorder. This would mean gravity weakens as the universe ages, a slow fade that could one day unravel galaxies themselves. The Milky Way's spiral arms, Earth's orbit, even the bonds holding your molecules together, all contingent on a force that might be evaporating as we speak. Critics argue entropic gravity can't yet explain all gravitational phenomena, like the precise orbits of binary pulsars, yet its implications are too profound to ignore. If validated, it would mean gravity isn't something the universe has, but something it does, a behavior emerging from deeper, more primal laws. The cosmos wouldn't be a machine following fixed rules, but a living, evolving entity whose very muscles, stars, planets, black holes move in response to its growing fatigue. So is gravity time's fingerprint. The answer could redefine reality. From the fall of an apple to the spin of galaxies, everything we consider fundamental might just be ephemeral, a cosmic phase, a temporary habit in an aging universe learning to let go. And in that realization, we glimpse a humbling truth. The force that grounds us, that sculpts the cosmos, might simply be the universe sighing as it stretches into middle age. The holographic principle doesn't just challenge our perception of reality, it shatters it. Imagine the universe as a movie screen where every star, planet, and atom is merely a projection from information encoded on a distant, two-dimensional surface. This isn't science fiction, it's a serious theory growing out of black hole physics, where the amount of information a black hole can hold scales with its surface area, not its volume. It's as if the cosmos is a grand illusion, a three-dimensional mirage flickering into existence from a flat, cosmic film strip. The implications are staggering. What we experience as depth, texture, and solidity might be nothing more than the universe's version of virtual reality, a rendering so seamless we've mistaken it for the real thing. Consider how your brain constructs reality. Light hits your retina, converting into electrical signals that your mind interprets as images, sounds, and textures. The holographic principle suggests the universe operates similarly. The information needed to describe every particle, every force, even your conscious experience, could be etched onto a boundary we can't perceive, like the event horizon of a black hole or the edge of the observable cosmos. Just as a hologram splits laser light to recreate a 3D image from a 2D plate, the universe might project itself from data stored on this primordial surface. The math checks out. Equations describing quantum gravity in a 3D space perfectly match those of a 2D theory without gravity, as if the third dimension is an emergent afterthought. But here's where it gets mind-bending. If the universe is a hologram, who or what is the projector? Some theorists speculate this could point to a simulated reality, where the cosmos runs on a computational substrate we'll never access. Others propose something even stranger, that the universe is self-rendering, a conscious entity perceiving itself into existence. This idea, dubbed cosmopsychism, suggests that consciousness isn't a product of the universe, but its foundation, that the cosmos isn't just aware but is awareness itself, with our minds as localized nodes in its vast neural network. The evidence is circumstantial but haunting. Quantum entanglement, where particles instantly influence each other across vast distances, mirrors the interconnectedness of neurons in a brain. The universe's large-scale structure, galaxies strung along filaments like synapses, echoes the architecture of neural networks. Even the holographic principles math resembles how brains compress sensory data into efficient, low-dimensional representations. It's as if the universe keeps rediscovering the same blueprints, whether it's building a brain or weaving space-time. So are we living inside a universal mind? The question blurs the line between metaphysics and physics. If true, it would mean every thought you've ever had, every memory, is a ripple in something far vaster, a cosmic stream of consciousness where reality is less a thing and more a thought. The night sky wouldn't just be a view, it would be a reflection, the universe gazing back at itself through countless eyes. And in that realization, we confront the most humbling possibility of all, that the cosmos isn't just alive, but alive in a way that makes our very existence a kind of cosmic self-awareness, a universe waking up to its own infinite depths. Boltzmann brains sound like something from a fever dream, conscious entities that could spontaneously flicker into existence from random quantum fluctuations, fully formed with memories, thoughts, even the conviction that they've always existed. The idea comes from a haunting question. In an infinite universe where entropy dictates disorder, couldn't sheer chaos occasionally arrange particles into a self-aware structure by pure accident? Not through evolution, not through the slow burn of cosmic time, but in an instant, like a lightning strike of awareness in the void. And if that's possible, how do we know we aren't one of those fleeting aberrations, here one moment and gone the next, convinced of our own permanence by the very illusion of memory? Think of it like bubbles forming in boiling water. Most pop instantly, but statistically, given enough time and energy, one might briefly take on the shape of a perfect cube. A Boltzmann brain is the cosmic equivalent, a freak accident of thermodynamics where particles align just right to create a conscious observer. The math behind this isn't fantasy. It's rooted in Ludwig Boltzmann's 19th century work on statistical mechanics, which showed that even in equilibrium, tiny pockets of order can emerge from chaos. Scale that up to the universe and the implications are terrifying. If reality lasts long enough, trillions upon trillions of years, the odds shift. A single self-aware fluctuation becomes not just possible, but inevitable. This isn't just a thought experiment, it's a direct challenge to how we perceive reality. If Boltzmann brains can exist, then the universe doesn't need galaxies, planets, or even time to produce consciousness. It could happen anywhere, anytime, in the cold emptiness between stars or the fading heat of a dead cosmos. Some versions of quantum mechanics even suggest these brains would outnumber organic observers like us by an unimaginable margin, making it statistically more likely that you are a Boltzmann hallucination than a product of 13 billion years of evolution. The irony is delicious. We use our hard-won intelligence to probe the universe's secrets, only to discover that the very act of thinking might be a glitch in the cosmic code. It's as if the universe is playing a joke on itself, generating observers who mistakenly believe they're uncovering fundamental truths, when in reality, they're just transient ripples in an infinite sea of disorder. But here's the twist. Boltzmann brains might reveal something profound about the nature of reality. If consciousness can emerge from randomness, then awareness isn't tied to biology or even matter in the traditional sense. It's a pattern, a specific arrangement of information that the universe stumbles into again and again, like a musician improvising the same melody across eternity. In that light, we're not accidents, we're inevitabilities, part of a spectrum of awareness that stretches from human minds to hypothetical quantum flukes. So is the universe dreaming us, maybe, or perhaps we're the universe's way of dreaming itself into existence, fleeting or not. Either way, Boltzmann brains force us to confront the fragility of our place in the cosmos, not as its pinnacle, but as one whisper in a vast, chaotic chorus of thought. And in that uncertainty, we find a strange comfort. The universe might not just contain consciousness. It might be consciousness, endlessly rearranging itself to ask the same unanswerable questions. White holes shatter everything we know about cosmic endings because they might not be endings at all. If black holes are the universe's relentless devourers, white holes are their theoretical counterparts, cosmic fountains spewing out matter and energy in a violent, radiant birth. Imagine a black hole running backward in time, its event horizon not a point of no return, but a threshold of expulsion where nothing can enter, only escape. These hypothetical objects aren't just mathematical curiosities. They're potential keystones in a grand cosmic cycle, turning destruction into creation with the elegance of a phoenix rising from ashes. The math behind white holes emerges from the same equations that predict black holes, Einstein's theory of general relativity. But where black holes collapse inward under gravity's crush, white holes explode outward, their interiors forever cut off from the outside universe except as a one-way channel. Picture a newborn star's fiery debut, except instead of gas and dust coalescing, it's space-time itself unraveling, birthing new material into existence. Some theorists propose that the Big Bang could have been the ultimate white hole event, a singularity not of implosion but eruption, spraying the seeds of galaxies into the void. Yet here's the haunting twist: white holes might not just be isolated oddities. If they exist, they could be the second half of a cosmic life cycle, where black holes swallow matter and white holes rebirth it elsewhere. This idea, called the black hole-white hole connection, suggests that when a black hole's evaporation via Hawking radiation reaches its final moments, it might transition into a white hole, recycling its trapped energy back into the cosmos. It's a universe-scale version of composting waste in, nutrients out, where even the most destructive forces are part of a larger, regenerative loop. The implications ripple across physics. If white holes are real, they could explain mysterious phenomena like fast radio bursts, intense, millisecond-long energy flares from deep space. These bursts, some argue, might be white holes clearing their throats, ejecting stored matter in sudden, luminous spasms. Even dark matter's enigma could be tied to these objects, with some theories suggesting white holes might eject invisible particles that weave the universe's hidden scaffolding. But the most profound question white holes raise isn't about mechanics, it's about meaning. If the cosmos truly cycles matter through black holes and white holes, then the universe isn't just expanding toward heat death. It's pulsing, breathing, reinventing itself across eons. Time becomes less an arrow and more a Möbius strip, where endings fold into beginnings. The atoms in your body might have once passed through a black hole's maw, only to be reborn in a white hole's glow, part of an infinite dance of dissolution and renewal. So is the universe alive in the most literal sense. White holes don't just challenge our definitions, they obliterate them. In a cosmos where destruction is just prelude to creation, where every exit is an entrance somewhere else, life and death aren't opposites. They're partners spinning the wheel of existence forward, one impossible transformation at a time. And if that's true, then the night sky isn't just a graveyard of dead stars. It's a nursery waiting for its next big bang. The silence of the universe isn't just eerie, it's deafening. With billions of galaxies, each hosting billions of stars and planets, the math suggests life should be everywhere. Yet the cosmos remains stubbornly mute, like a crowded room where no one speaks. This is the Fermi paradox in a nutshell. If the conditions for life are so common, why does Earth feel like the only inhabited island in a vast, empty ocean? The answer might not lie in the stars, but in the nature of life itself, and whether the universe is even capable of recognizing its own reflection. Consider the sheer scale of time. Earth has harbored life for nearly 4 billion years, but human civilization, a blink just 10,000 years, radio waves, our first cosmic hello, have barely traveled 100 light years. In a galaxy 100,000 light years across, our signals are less than a whisper. Now imagine another civilization, just slightly older, their signals sweeping past us millennia ago or yet to arrive. We could be ships passing in an ocean so vast our wakes never intersect. The silence isn't proof of absence, it's a testament to the crushing immensity of space and time. But what if the paradox runs deeper? Life might not be rare, it could be ephemeral. Civilizations could rise, bloom, and vanish like fireflies in the night, their existence too brief to overlap with others. Imagine a galaxy where 1,000 civilizations have come and gone, each lasting just a few thousand years, the odds of two being active simultaneously. Almost zero. The universe might be a graveyard of self-awareness, littered with the ruins of minds that ask the same question we do, only to fade before finding an answer. Then there's the darker possibility. Life might be its own undoing. Intelligence could carry the seeds of destruction, whether through war, environmental collapse, or technologies that outpace wisdom. The Great Filter, a hypothetical barrier preventing life from reaching the stars, might not lie behind us, but ahead. Every civilization that unlocks atom splitting or artificial intelligence might unknowingly race toward the same cliff edge, leaving the cosmos littered with silent monuments to their hubris. Yet the most unsettling answer of all, we might be alone. Not because life is impossible, but because consciousness is a fluke, a single spark in an endless void. The universe could be teeming with microbes and moss, but self-aware minds like ours, a 1 in a trillion accident. If true, we're not just inhabitants of the cosmos, we're its only witnesses, the universe's solitary attempt to understand itself. The weight of that responsibility is staggering. Every song, every painting, every equation we've ever written would echo in an abyss with no one to hear. But here's the twist: the paradox itself might be a kind of cosmic communication. The silence isn't empty, it's a message. It tells us life is fragile, rare, or perhaps so advanced it's unrecognizable. Maybe civilizations don't broadcast radio waves. They transcend into digital minds or higher dimensions, leaving the physical universe behind like a discarded shell. Or perhaps they're all around us, watching, waiting for us to reach a maturity threshold before making contact. The universe's quiet could be the ultimate test, a filter not of biology, but of wisdom. So are we alone? The answer might not matter as much as the question itself. In asking, we've become the universe's voice, turning its silence into a dialogue. Whether we're the first, the last, or the only, our very curiosity stitches us into the fabric of something greater, a story still being written, one lonely, courageous thought at a time. The simulation hypothesis doesn't just question reality, it rewrites it. Imagine the universe as an unfathomably advanced computer program, where every star, every atom, even your thoughts are lines of code executing in a cosmic processor. At the heart of this idea lies a startling observation: the quirks of quantum mechanics, particles existing in multiple states until observed, entanglements, instant connections across light years. behave less like natural laws and more like programming shortcuts in a vast simulation. It's as if the universe is running on hardware with limitations, its rendering engine only calculating what's necessary to maintain the illusion of continuity. Take quantum indeterminacy, where particles lack definite properties until measured. In a simulation, this mirrors lazy loading, a programming trick where details are generated only when needed to save processing power. The double-slit experiment, where particles act as waves until observed, could be the universe's version of graphics optimization, only rendering the full image when a player or consciousness looks. Even the Planck length, the smallest meaningful unit of space, fits eerily well as the pixel size of reality's grid, a resolution limit baked into the cosmic code. But the evidence doesn't stop at quantum weirdness. Glitches in the cosmic matrix might already be visible. High-energy cosmic rays with inexplicable energy levels, like the Oh My God particle detected in 1991, could be buffer overflows errors where the simulation briefly exceeds its allocated memory. The universe's uniform temperature in opposite directions, a puzzle called the horizon problem, might not require inflation theory but could instead reflect a shared initialization value, a default setting baked into the program's startup sequence. The most provocative clues come from mathematics itself. Our universe's laws are inexplicably describable by equations, as if reality runs on elegant, compressible algorithms. Physicist Max Tegmark argues this unreasonable effectiveness of mathematics suggests the cosmos is fundamentally computational. Even consciousness, that ineffable spark of awareness, might not be emergent but primary, the user interface through which the simulation experiences itself. After all, in a virtual world, what's more real, the rendered objects or the observer who gives them meaning? Critics dismiss this as modern-day solipsism, a high-tech repackaging of Descartes' evil demon. Yet the hypothesis gains traction from an unlikely source, our own technological trajectory. Humanity has already created immersive virtual worlds, from video games to AI-driven simulations. If our civilization can build rudimentary universes in silicon, why couldn't a more advanced creator do the same? The argument isn't proof, but it shifts the burden. In an infinite cosmos, the odds that we're the base reality shrink uncomfortably. So what's at stake? If the simulation hypothesis holds, everything from free will to the nature of death transforms. Your memories might be saved files, déjà vu, a glitch in their retrieval. The laws of physics could be mutable, patched, or updated by unseen programmers. Even the boundaries of life and death blur, as consciousness might persist as reusable data in some cosmic cloud. The universe becomes less a brute fact and more an artifact, a crafted experience with purposes we can't yet fathom. Whether terrifying or exhilarating, the simulation hypothesis forces a reckoning. If reality is code, then the greatest discovery wouldn't be extraterrestrial life or unified physics. It would be the compiler's signature, the telltale keystroke left in the cosmic script. Until then, we're left with a haunting duality, the universe as we know it, and the unsettling possibility that we're not just players in the grand game, but lines in its source. From pulsars to plasma, from the cosmic web's neural-like filaments to the rhythmic breathing of stars, the universe doesn't just resemble life, it performs it. Everywhere we look, the same patterns repeat, as if nature has a favorite blueprint. Branching fractals in galaxies and capillaries, self-regulating feedback loops in black holes and cells, even the eerie synchrony of quantum entanglement mirroring the silent communication of neurons. But here's the million-light-year question: are these similarities profound clues or just cosmic coincidence? Consider the sheer improbability of it all. The universe could have been a featureless void, a monotonous expanse of particles drifting forever without structure. Instead, it's a dynamic, self-organizing tapestry where energy flows, information transmits, and complexity emerges against all odds. The same mathematical rules that govern the spin of planets also dictate the growth of sunflowers. The same efficiency that shapes river deltas arranges galaxy clusters. These aren't just pretty parallels, they're fingerprints of something deeper, a hidden grammar weaving everything together, yet skepticism is healthy. Humans are pattern-seeking creatures, wired to see faces in clouds and agency in the wind. Could we be projecting our own biology onto a universe that's fundamentally indifferent? After all, stars don't think, they fuse. Black holes don't decide, they consume. The cosmos operates on physics, not intention. But here's the counterargument. Life itself emerged from these same impersonal laws. If atoms can arrange into beings who ponder their origins, then perhaps the universe's aliveness isn't a binary yes or no, but a spectrum with consciousness as just one vivid point along an infinite gradient. The implications are staggering. If the universe behaves like an organism, then we're not just inhabitants, we're expressions of it, fleeting thoughts in a cosmic mind. Every time a pulsar's beat matches a heartbeat, or a galaxy's spin echoes a cell's division, we're glimpsing a unity that transcends scale. Conversely, if these parallels are mere illusions, then the fact that we can imagine such connections at all becomes its own miracle. Either way, the mystery reshapes our humility. So where does that leave us at the edge of awe, staring into a cosmos that refuses to be neatly categorized? Whether the universe is truly alive or just lifelike, one truth remains. We're part of something far grander than we've yet comprehended. And that's the real gift of these 36 parallels, not answers, but better questions. Now it's your turn. Do you see a universe that's conscious or one that's simply convincing? Drop your thoughts below, and don't forget to subscribe for more journeys into the unknown. Because the greatest wonder isn't just out there, it's in the conversation we're having right now.